All right, so we're continuing with class 3 in fluid mechanics. This is video 4 for this class, and we're going to talk about manometers, right? So we have a few representative manometers right here. And as we mentioned, there could be a little bit confusing. So here's some real manometers as opposed to just these pictures of ones. Sometimes, you know, if the pressure difference we know in the application is going to be big enough, if we're going to use water inside a manometer, we might actually come in a coil like this. This is a pretty common thing. Maybe you've seen these before. And if the pressure, I'm giving away like something I ask later, but that's okay. Sometimes we'll have them on an incline. This is to measure very, very small differences in pressure. So sometimes we might want to measure a pressure compared to atmosphere, or other times we might want to put it on either side of something that's maybe with air flowing through it. And so one of the means that is very, very common to try to measure whether a filter, an air filter, is getting dirty is to connect a manometer to either side of the filter. And so there's pressure on one side, and then there's the pressure on the on the exit of the filter. And as that filter gets dirty, that differential pressure increases, and then you can tell by way of the manometer, of course. And that could be a very, very small incremental change in pressure. So the manometer is really useful for that. But so these are different ones, and I think maybe if you go to the aerospace turbine engineering lab that's over in the Hersey Center, I think Dr. Slaybach has manometers on a lot of things over there, because that's a pretty common thing to use to measure small pressures. Okay, so let's see, we'll go over to the document camera here. And so here's that fundamental equation that we had talked about when looking at to try to figure out the pressure in tanks as we go downwards for static fluids. And so here's our analysis method here. We're going to swim through the manometer to try to find. But the convention, though, we want to use in that swim through, so we start at the outside, we start at one particular spot. Quite often we'll start at where the atmosphere is. And the convention we want to use is when we're swimming downwards, we're going to make that positive, and when we swim upwards, we're going to make that negative. And anytime there's a difference in specific weight, we're going to create a new term. Right, so we might add, there might be multiples of these if we're going through different densities of liquids. And then when we arrive at the thing, we'll say this is the pressure, right? So we'll start here, we'll swim downwards and add these in here. Anytime we're swimming down, we'll be adding. Anytime we swim up, will be negative. And then we're going to get to our destination, which is the pressure, right? So that'll help us keep track when we can get sort of the confusing versions of the thing. So here is how we're using it right here. So this is, you could picture this right here. What they're showing here is this is like a pipe that's been cut, and someone has drilled a hole inside here into the side of the pipe, and they put off this little tube, and maybe the pipe is glass, or maybe somehow that they've kept this as glass so that we could see inside it right here. This is not a very smart way to measure pressure, because if this pressure fluctuates too much, it's going to start spewing out right there. But hopefully the pressure is not so large in here that this has to be really tall in order to measure it. But this is weight. You could measure it, but you probably wouldn't. So if this is, like, say, PO, that's the atmospheric right here, and this is A, and so this is the level at which we care about, right? Not at the bottom, not at the top. It's the same level as this spot right here. We're going to say that PA is going to be equal to P1, because they're on the same level. And we're just going to take the gamma of whatever this is. Okay, they're saying gamma 1 right here, and then H1, and they're going to add in PO, right? So we like started here, and then we added gamma 1 and H1 to it. But so here's another scenario right here where we have two separate liquids. And let me see if I can get this to, let's see, that helps, okay. So right here is our atmospheric pressure right there. And remember, we're swimming downwards. And so this density right here of this, it has to have do you want to say it has to be more dense? Yes, it needs to be denser than this to be, for this to float on top of that, right? That's an important thing to recognize. So we're going to go and we're going to call this, I decided to call this gamma 2, and I call this gamma 1, just arbitrarily, right? So we start here at P0, and maybe I'm going to write out, this is A right here, so PA is going to be equal to P0, and we're swimming down, so it's going to be plus, and we don't have to count this bottom part right here. It only matters where we make the change right here. So it only matters to the interface. This is the one that we care about right here. So that's going to be gamma 1 times H1. But then we're going to swim up to get to this level right here. So it's going to be minus gamma, I'm sorry, this should have been 2. My bad. This is H2. I can't even read that. It says H2, yeah. My poor eyes. So gamma 2, H2 as we're swimming down, and then we get to this level, and then we start swimming up. So it's gamma 1 and then H1. But it's negative because of that. And that's going to get us the desired pressure. So we start out with atmospheric, swim down, swim up, get to the spot that we want. And let's see, we have a couple other examples right here. So we're going to swim. So here is one where we have like a differential between two separate pipes, and the pipes are at different levels right here. And so this guy over here is kind of telling us how we would go about. Maybe we'd start at, actually I don't even know if that thing is something I want to talk about. Maybe I don't. You know, I don't like this diagram right now. Not liking the diagram. So I'm going to ignore this diagram. I don't even know what he's doing there. Yeah, I don't think he's correct, at least off the top of my head. So we're dealing with a pressure difference, and we're going to go from start at B, and we're going to go to A, right? So we're looking to find A. So start at B, and we're going to swim downwards, and we'll call this gamma 3. Right? Is that already listed somewhere? I don't think so. Yeah, no, there it is right there. Gamma 3, yeah. Now here's the gamma 2. And then this is already showed as gamma 1, right? So it's already done first. So we go down. Oh, gamma 3. And here is H3. And then we're going to keep swimming down from here to here. So that's going to be plus gamma 2, H2. And then we're going to swim up to get here. So this is a different liquid. So I go minus H1, gamma 1, H1, right there. And we could actually, if we wanted to, go the other direction if we wanted to, right? So sometimes we might want to say a delta P, like what is the difference between A and B? Probably the way to go is, so let's go the delta AB, we'll go A minus B right over there. And then of course is going to be gamma 3 H3 plus gamma 2 H2 minus gamma 1 H1. Or we could do the other thing right here, and we could say, we could have gone the other direction, right? We could have said, well, maybe we want to go from A, if we want to go from A to B, right here, we would say starting at B, starting at A, because we want B, so we're going to start with B, find B by starting with A, and then we're going to swim down, minus, no, that's plus, we're going to plus because we're going down, so we go gamma 1, H1, and then we're going to swim upwards, so we're going to have minus gamma 2, H2, and then swim upwards and go minus gamma 3, H3. And then, if we wanted to have A minus B now. So we're going to go delta PAB, which is the same thing as we had right up there. We would say PA minus PB. So now PB has to come up this side. All these have to come on the other side, and we would get the identical thing, right? We would get positive right here, and this becomes positive because it's going to go on to the other side. I guess that seems pretty apparent, but just trying to organize our method right here. That we could start at either spot, and so sometimes we want to have the delta between them. And how am I doing? Can I finish all this? I think I can. I'll go ahead and finish it. So this is all the manometers. I only have one page after this. So if you have an inclined, and the reason why we do the inclined is then just like as we saw in the in this guy right here, you can see that now we could actually look really closely, and maybe at the mid mark of whatever little tiny meniscus this would be. We could. This is just one. This is a differential of 1 single inch of water, and they put like a food coloring in there that you would assume doesn't change the density, because otherwise that would be no good. So what we could do here is, if we were trying to measure PB, we would take PA as the reference, swim downwards through this. Of course, this needs to be gamma 1 if that's H1, and we're going to assume that this is gamma 2, and whatever this is gamma 3. So we'd swim down and say plus 8 gamma 1 H1, and then subtract out, because we're going to start swimming upwards, but it's really from about there that we're measuring right there, right? So they're calling this, it looks like a B, but I think this is L2 actually right there. So we take gamma 2 and take L2, but now it's only the vertical part of it. So here is theta is the angle, so we're going to take the sine of theta right in there, and we're still swimming up, so it's going to be negative, and so we're going to have gamma 3 H3. And that's how we would use the inclined manometer. And the Y is because it might be such a small pressure difference that if it was just a vertical manometer, we wouldn't be able to read with enough precision. So here you go. Here's 2 examples right there with actual numbers. It says 2 pipes are connected by a manometer. Determine the pressure difference PA minus PB in the 2 pipes. So I would say start out with PA is equal to PB, and so we're going to start at B and get to A right there. So we start at B and swim upwards, and so that's going to be negative. And we'll call this one. This is water. Gamma 1 is water. Call that H1, and this difference right here is going to be equal to H2, and whatever this liquid is, it's got a specific gravity of 2.6, and then the rest, and then this is water right here, right? So we'll call from here to here is going to be H3, and even though it's the same as this, we'll also call this gamma 3, right? So just to keep track of stuff. So we're swimming upwards as negative gamma 1, come on silly, gamma 1 and H1, and we're going to get up to this spot right here. Whoops, gotta be careful here. This should be H1 right here. So I went too fast. This is H1, sorry. So not that one. And so that's okay, that's right. So we get to this spot right here, and we don't really care about this stuff right here. This doesn't play, it has to be at the same level of the interface. So we're going to swim downwards, and that's just going to be our gamma 2 H2, and then we're going to swim upwards again to get to A. So we're going to take gamma 3 H3. So now let's throw some, and now because we were looking for PA minus PB, we have PA minus PB, and we could just proceed with this, right? So let's go ahead and use metric. And so I took that minus, I put it right there because I didn't leave myself enough room. 9.810 kilonewtons per cubic meter times, and we're going to go up 1.3, but we have to subtract out that 0.5 so that we're dealing with H1. So that ends up with 0.8 meters, right? And then I didn't leave myself enough room, so I'm going to come down to there. We're going to have specific gravity at 2.6. So just take the specific gravity and multiply it by our 9.81. We could put the units on there, but we know that this is kilonewtons per cubic meter. And then the distance that we have is going to be 0.6. And still not leaving enough room, so we're going to swim upwards, minus, and now it's once again 9.810 for the water, and the head level here, from here to there, is going to be 0.6 plus 0.5, or 1.1, right there. And so doing all of this, we end up finding we get a negative number, right? So that means that A is going to be less than B, and we'll get 3.335, and that should be, I'm taking a look at this right here. That should give us a pressure in kilonewtons per meter squared, right? Because meters times cubic meters, and so that's the answer right there. So go at delta P AB, and I'm saying that it's A with respect to B. Maybe I could call it that. I'm not sure. It's going to be a negative 3.34 kPa differential. And here's one that's kind of confusing because of the arrangement. So, but if you just methodically go through it, you got no problem right here, right? So this one has carbon tetrachloride. So we need the density, the weight density of that. I'll look it up for you, but I believe it is in the equation sheet for the exams. 99.5 pounds per cubic foot. And because we're dealing with US units, we'll use that. And this is atmospheric right here. So I think I decided to swim from this direction over to the atmospheric, right? Okay. Because I haven't read the problem yet. So this is it. We're calling this an inverted manometer right here. And we have we have some kind of gas pressure inside this that's giving us 8 psi. And we can assume that that's gauge pressure. So it's psi-G. And carbon tetrachloride, we know this. And then there's some kind of oil right here that has a specific gravity of 0.8. And the reservoir onto the left, carbon tetrachloride, is closed, right? So it has a pressure in there. The reserve on the right contains water and is open to the atmosphere. That's what they mean right there by the way it looks. With the given data, determine the depth. All right, so we've turned this problem around a little bit, but we can, if we just follow our procedure, we're going to be good. So what we want to do here is start out here and end up there. So we're going to do is going to say the atmosphere is going to be equal to, I'm just going to go ahead and use the numbers instead of trying to come up with symbols for all these, but we know that we're going to have 8 psi, but I'm going to do everything in feet right here. So I need to turn the psi into pounds per square foot. So I'll take my 8 and multiply by 144. So now this result is going to be pounds per square foot instead of pounds per square inch. And I'm going to swim downwards, but I'm only going to go this level right here. Actually, all I need to do is go this level right here. Right? So I only need to swim down that amount because we're going from the top of this to this interface right here. So the weight density of this, as we said, and we're swimming downwards, so we're going to add 99.5, and we want to get the distance between here. They say this is 3 feet, and so we need to subtract out 1 plus 1 plus 0.7, or subtract out 2.7 right there. Great. So that's the distance right there. It's only going to be like 0.3 feet is the distance right in there. And then we're going to go from this level, we're going to go downwards to this level, right? I know it looks like we're going up, but we're actually going down. So go plus down. And so the density of the oil, they gave us the specific gravity of 0.8. And so we're going to deal with water. So that's going to be 62.4, yeah, 62.4 pounds per cubic foot. And this will give us the weight density of the oil. And then we're only going to go down 0.7 feet, right? So we're going to go to there. And now, last part is the amount of water to get back up to the thing we wanted to get. And we're going to swim upwards, so it's going to be negative, and I ran out of room, so we're going to come down to the next line. And we're only going to be coming up this H, right? So we're going to go 62.4, and then it's going to be this distance right in here is going to be H minus 2 feet, right? Because that's the level right there. So it's minus 2. And let's treat atmosphere like it's 0, because everything, well, we're assuming, because this was gauge pressure, that's why we used gauge as the reference right here. So the atmosphere is considered 0, and we're able to solve for the H is 21.6 feet. So systematically, just using the swim through method, we're able to solve manometer problems, even more complicated manometer problems, and thus ends class 3. Whew.